So there's another method of finding these middle k% of a normal distribution that I want to show you right now. So generally speaking, we may not always be interested in a 95% middle. We could maybe be interested in 85 or 99, etc. So I'm going to represent this as a middle k%. And the approach we're going to use is something called the margin of error approach. And the reason I'm showing you this is because a lot of statistical techniques use this margin of error approach inside of their formulas rather than, say, working directly with like a Q norm like we did in the previous problem. Okay, here's the general idea. If you have a distribution for X bar, you want to find the middle k%. You know exactly where the middle of that distribution is going to be. It's going to be at the mu. It's going to be at the mean for your normal distribution. And what we want to know is essentially how far do we have to move from mu to get to the right hand and the left hand points that kind of define this middle k%, right? So we want to think of this distance as something called the margin of error. We know that since the normal distribution is nice and symmetric about mu, the distance to get to the right will be the same as the distance required to get to the left. It turns out that the margin of error formula, and we'll derive this in a bit, depends on a couple of things. So first of all, it depends on sigma, which is the standard deviation, sigma over square root of n, which is the standard deviation of this X bar distribution. And it depends on something called z alpha over 2, okay? So z is referring to the standard normal distribution. Alpha over 2 is essentially referring to the area that's sitting to the right in one of the right tails, okay? So we've got k% in the middle. Alpha is going to be the missing percent, so that would be in white. And we're going to divide that in 2. So we're going to have alpha over 2 in each one of our tails. So we're saying there's a special standard normal value, or z-score value, associated to that alpha over 2 measure. And in fact, we define z alpha over 2 as the z-score, right? So this is a value from the standard normal distribution with an area of 1 minus alpha over 2 to its left, right? So if we have alpha over 2 in this right-hand tail, the area to the left will be 1 minus alpha over 2. The way we're going to compute this is going to be using Q norm 1 minus whatever our alpha value is over 2. And then since it's a standard normal, a z-score, value, we're going to use parameters 0 for the mean and 1 for our standard deviation. Okay, so let's see why this thing works. So first of all, note that under our original assumptions, this X bar random variable is normally distributed. It has a mean of mu and a standard deviation of sigma over square root of n. And essentially, if we transform this thing by recentering it, subtracting mu, and then scaling it, dividing by its standard deviation, what we get is a random variable that's normally distributed with our standard normal parameters, so a mean of 0 and a standard deviation of 1. Okay? So here's the z distribution. Here's our standard normal distribution. Its mean is at 0, which makes this normal distribution perfectly symmetric. And if we have k% in the middle, if alpha is the missing percent, so that would be the percent in both the tails, then each tail is going to have alpha over 2. And our margin of error is just going to be a percentile for this z-score. Okay, so in other words, we're going to figure out what's the area to the left of this right-hand z-score. And the area to the left would be 1 minus its area to the right. So this will be a z-score with 1 minus alpha over 2 to its left. Okay, and that's exactly how we defined the notation z alpha over 2. Okay. Now, since we're perfectly symmetric about 0, since this is a standard normal distribution, the mark of the beginning of your middle k% is negative z alpha over 2 on the other side. Okay, so you can see that this single distance speaks for both. And the idea here is that the probability that a randomly selected value from your standard normal falls in between negative z alpha over 2 and z alpha over 2 is exactly equal to k%, or another way of thinking about this is 1 minus alpha, which is the area in the two tails. Okay, so here's how we derive our result. We know that a z-score falling in between these two values, z alpha over 2 and negative z alpha over 2, right? The probability of this is going to be 1 minus alpha, the probability of that occurring. Using this transformation, we can actually substitute in our transformed version of our X bar. And now what we can do is just try to get X bar by itself. So the first thing we would do is multiply through by this standard deviation that occurs in the bottom of our fraction here. So multiplying through by sigma over square root of n, we get the following equivalent inequality. And here you can see the margin of error formula starting to appear, right? Here's the special z-score. Here's the standard deviation of the normal distribution for X bar. And now all we're going to do is add mu to all three of these to get X bar by itself. Okay? So here we have this inequality, which held for our standard normal distribution, is equivalent to the following on X bar random variable. Mu minus z alpha over 2 sigma over square root of n, and then we have mu plus z alpha over 2 sigma over square root of n. So this equality and this inequality are exactly the same. Okay? Now, the general idea then, since we know this inequality here was set up to have a probability of 1 minus alpha, right, which is really our k%, the middle percent we're looking for, we essentially get the following result. So this probability of 1 minus alpha, or k%, is equal to the probability that a z-score falls in between these two values, which we can transform back to say the probability that our X bar random variable falls in between these two values. Okay? So in other words, the way that we create the left-hand point and the right-hand point, right, the way that we create the 6.887 and the 7.122 from our previous example, right, this left-hand point and the right-hand point depends on the middle of our distribution, and then we're either going to add or subtract this term, z alpha over 2 times sigma over square root of n. And this is what we call our margin of error. So the general idea is, here's mu, it's the middle. We're going to move z alpha over 2 sigma over square root of n to get to the right-hand point, and we'll subtract that amount to get to the left-hand point. So this is the more general setting. And the benefit of this is we get to use essentially the same qnorm command or to determine this z alpha over 2 value. The only time that this will update is if we're changing the middle percentage that we want to consider. That will have an effect on what's the area in the tails, or our alpha value. We'll cut that in half and we'll have to update slightly. But for the most part, what this is doing is sort of standardizing a process where the margin of error depends only on the percentage you want in the middle and the standard deviation, sigma over square root of n in this case, for that sample mean random variable X bar. Oops. So let's go over another example. So we'll jump into R. We're going to look at example 2. So we consider samples of size 35 from a normal random variable with a mean of 50 and a standard deviation of 10. We want to find the middle 99% of the sampling distribution for our X bar. All right, so keep the following steps in mind. So the margin of error approach has the following steps. All right, first, determine the middle percentage. Okay, so in our case, this is 99%. Right? This makes alpha equal to whatever's missing. So in our case, this is 1%, which is 0.01. Generally speaking, we're going to want to work with decimals rather than percentages. Okay? So in other words, we now know what alpha is. This means our alpha over 2 value is equal to 0.01 divided in half. So this will be a 0.005. Okay? All right. So up until this point, we've pretty much just done some basic algebra. Now we find our special value from the standard normal distribution, and we call this thing z alpha over 2. That's how we denote it. You can use your own keyboard shortcut or however you want to represent this. So we find this thing. This is also sometimes called a critical value. You'll hear that language as well. After we're done finding that critical value, we're going to find the margin of error. Now in our case, the margin of error is equal to this z alpha over 2 times our sigma over the square root of n. So again, and then our last step is the middle, in this case 99% interval, is simply going to be, we'll take that margin of error and we'll add and subtract it to the original mean. So this would be, as an interval, 50 minus the margin of error and 50 plus the margin of error, because 50 was the original mean. Okay, so let's do these steps, but let's do them below an R. And we can, if you want to, just kind of define some terms. So let's make alpha equal to 0.01. So clearly, if we took alpha over 2 and we evaluated it, we would get the 0.005 from before. Now let's find z alpha over 2. Now you don't want to actually, you don't want to use the division sign because that's going to have R try to actually do the division. So I'm going to call this z crit for z critical value. And remember, the general idea here is we take q norm 1 minus alpha over 2. Right? This is the area to the left of the appropriate z-score. If we go back to our original z-score picture. Right? This is the area to the left of the z alpha over 2 term that we want. And since it's a z-score, since it's a standard normal value, we put in our appropriate standard normal mean and standard deviation. So this is z critical. Right? We can define our margin of error. This is z critical times, now we would take our sigma times our standard or sigma divided by our square root of our sample size. So in this case is going to be 10, right? This is our original standard deviation. And we're going to divide by the square root of 35. And then lastly, our interval is going to be simply 50 minus margin of error, 50 plus margin of error. So if we run this whole set of stuff, we can actually erase the alpha over 2 at this point, or just comment it out is fine. Let's run this again. We'll get the start and the stop of our middle 99% interval for this random variable x bar when we were randomly sampling from a normal distribution with a mean of 50 and a standard deviation of 10. All right, so here's the idea. So this means that 99% of the time, the sample mean random variable x bar will have a value that falls between our 45.646 and 54.354. Okay, so it's giving us an interval where our sample mean random variable is going to fall 99% of the time. So this is the most likely range of values for our sample mean random variable. Okay. Now what I want to do, just to reinforce this idea that this is where our sample mean tends to fall, is I want to simulate what we found above. So here's what we're going to do. We've done something similar to this in the past. What we're going to do is, first of all, define a function. Let's call it getMean. And it's going to have parameters n, mu, and sigma. And what it's going to do is essentially find the mean of n observations from a random, normal random variable with parameters mu and sigma. So we're going to collect n of those. We're going to take the mean of them, and that's what we're going to output. Okay? Now what we want to do is let's collect, say, 5,000 different sample mean observations. And we'll use the parameters n equals 35, mu equals 50, and sigma equals 10, all right, to reflect our previous situation, right, to reflect example 2. So we do this in the usual way. Collect obs. We'll set up a numeric variable with 5,000 spaces, right? So currently it's all zeros. So we'll do for I in 1 to 5,000. And now what we want to do is, as we loop through those values of I, we're going to replace the ith component of this collect obs variable vector with an observation of this get mean. So this would be n equals 35, mu is equal to 50, and sigma is equal to 10. Okay, and now what we'll have is a collect obs vector. And if we want to, we could take a quick look at the histogram for this. So let's run all of this information. We've got a nice histogram of these sample mean observations, and we can see that for the most part, 99% of the time, we should be between 45, which is about here, and what was our other bound? 54.3, which is up here. But we can do one better, right? This collect obs variable contains all of the sample mean observations. So let's check how often collect obs is below our lower limit. So 45. I'm just going to copy and paste this, might be easier. Right. And when I do this, I'll get a bunch of, I'll get a big long logical vector, but remember you can sum your logical vectors to count up how many of these end up being less than our lower limit there. And I'm going to do the same thing, but this time I'm going to look at being greater than my upper limit for that 99% interval. And what I'm actually going to do is add these two things together. So this will count how many of my sample mean observations were below the lower limit and how many were above the upper limit, and then add them together. And I get 47 in total. All right. Now what I'm going to do is divide this by the total number of observations that I collected. So if I divide this by the total number, I get essentially 0.0094% of my observations fell outside of my interval, right? So if I take 1 minus this value, it'll tell me what percentage of my observations fell inside of the value, fell inside of that interval. And you can see that it's essentially 99% of them, okay? So this probability we can simulate using actual observations. If you generate a bunch of observations, roughly speaking, 99% of the observations should fall inside of this interval. Does this make sense? So this essentially counts up, we're using the 1 minus trick here to count the percentage of observed sample means that fell inside our region, our, let's call it 99% region computed in part A. Okay, and again, the idea is the theory, right? Using this middle percentage theory gave us an interval to shoot for, and then we simulated this by collecting 5,000 sample means, and we ended up with an observed 99.06% fell inside, right? So you can see that the theory and the simulation, the observations are matching up.